domain which is called S domain. In order to go into that domain, we've got to know what Laplace transform is. So this chapter is related with Laplace transform. This is not, I assume that this is not the first time you are facing with the Laplace transform. Most probably you have seen that in differential equation course in order to solve the differential equations. Now in here, we are dealing with special functions that we see in circuit theory. So we will be concentrating on these special functions and their Laplace transform in this chapter in more detail. So let's start with why we need a new domain, S domain. Because frequency domain has got some restrictions. You might remember these restrictions. Sources must be sinusoidal only. Homogeneous solution cannot be found. Another name of it, transient solution, cannot be found. Natural solution cannot be found. Natural solution, you might remember it, is the one where initial conditions are in, but independent sources are deactivated. The forced solution cannot be found in this domain, in frequency domain I mean. Forced solution, as you remember, is the solution when the independent sources are in, but the initial conditions are 0. And the last limitation is the stability cannot be determined in frequency domain. So that's why we need a new domain. New domain is S domain. In S domain, there is no restriction like that. So therefore has got a superiority with respect to frequency domain. Then you might ask why we need a new domain then, or why we need frequency domain anymore. So teach us only one domain. The reason is this: in Laplace domain, transform between T domain to S domain or from S domain to T domain takes a bit time. But the in frequency domain transformation, that means from phasors have to find the time function, how to transfer the time function, which is sinusoidal function, to a phasor, is easy transformation. So it has got some priority on the transformation side. Therefore, we need both domain in practice. So the question is it possible to analyze linear circuits by algebraic equations with no restriction? Yes, it is possible if we use the time domain. If we use S domain algebra. So remember now definition of the Laplace transform. If you've got a ft function, which is the function of t, the Laplace transform of this function, which is the capital Fs, is the integration, boundary integration of ft after multiplied with e to the power minus st, and integration is taken on t. So the conclusion of this integration is not to depend on t anymore because of these boundaries here. So if you put these values in it, then it becomes a function of s. So this is Laplace transform of ft. So if you've got a Laplace transformed function in S domain, so you've got to transform this function to time domain function, because time domain is the real domain. This is the domain that we could interpret the results. These limitations here are the mathematical limitations on that integration. some functions Laplace transform may not exist. That's normal if you cannot take this integral somehow, or the result of this integral is infinity. So that means that functions Laplace transform function do not exist. But in circuit theory, for the circuit theory functions that we deal with, there is no any problem like that. All these functions Laplace transforms are available. So I would like to mention one more additional subject in mathematics in here. It is unit function. The unit function is important. I will explain it in details later on, but in first step, definition relation is this: if t is smaller than 0, if you consider k equal to 1, so ut, that's the unit function, is equal to 0. So as you see it, this area. If t is bigger than 0, then assume that k equal to 1, then ut is equal to 1, so it is the right hand side. So it is like a switch, isn't it? That's off, that's on. Position of the switch. So this switch is a practical element in practice that you see that. So you can represent this unit, that switch, by this function. So you can say that when t equal to less than 0, the switch is off. That means the sources are not connected to the circuit, to the equipment. When you switch it to on position, so independent sources are connected to the equipment. So all the electronic equipment has got that switch on it. So this is the mathematical model of that switch. We can play with that function, saying that if you replace t with t minus a, that means you move or shift your function to the right hand side. When there is a minus here, that shift becomes to the right hand side. We have seen similar things in the sinusoidal functions related to the angle that we add. So if you change the angle, if you add a constant to the angle of your function, sinusoidal function, your sinusoidal function moves right or left. So that is shifting related to that application. So here you are. If you move this function to the right hand side by a minus a, you get this function. So this function, if you replace t means a minus t, it becomes this function. So this function is important. We said because it becomes a switch. Let me explain that switch business and then how we can represent some of the special functions by using these unit functions. So I should move to open board now. And open board. Here are. So these are the unit functions we've got. We are saying, let me explain in this area, the switch. So let's say you've got an independent voltage source here and a switch here and an equipment here. So this is off case, isn't it? So that means there's no current passing through to the equipment. This is electronic equipment. If there is no current passing through, that means there is no any energy that you apply to the equipment. So all the elements, current and voltages, are equal to 0, isn't it? Let's say this is Vs. this Vs could be either a DC source or AC source or any source. So if you switch this switch to the on position, as soon as you apply to the on position, that means you change from 0 to this. So let's say this happened when t equal to 0. So you are applying that Vs directed to your equipment. That means this energy comes in, so all the elements, current and voltages changes. So this switch now is the representation of this function. Or this function represents this switch behavior in physical world. So I said this is also useful in order to represent some functions which are available in practice. For example, consider this function. This function, you can see the function is active between 0 and 4. After that it is 0. So it's just one function. If you can write this function, can we write this function as a formula? No, we cannot write it. But we can represent this mathematically by saying that f is equal to ft is equal to 2t if t is in between 0 and 1, and you can write it like that. So the question is, can we write this function as a formula? The answer is yes. You can write it as a formula like that by using the unit functions here. So how we are doing this, let me explain to you. So I should start with a pulse function. Let me explain what pulse function is. Here. Unit pulse function, let's assume this. So change the color here. So this function here, this blue one is pulse. If this is 1, so okay, change this. 1. So this is pt, pulse function, that's t. So how you can get this pulse function, let me move this one towards here. So I am saying I can get this pulse function by using these functions. Assume that k is equal to 1. So k equal to 1. So when k is equal to 1, so it becomes yt. Yt is called unit step function. Okay. Now I'm saying this is ut minus a. So if you write the negative of this, so this is ft is if k equal to 1, so it is ut minus a. So I am asking now minus, let me make it a bit better, maybe different color. Now here, and this one, minus UTA, so this is A. So when it is minus, it's going to be like that. Just a moment. So that's okay. So this is this function, isn't it? So this function that is ut. Now this function, negative of this function is going to be up to a. Let's come to this like that. It's going to be 0, like this. And then, let's make it yellow. It's going to be like this, isn't it? Maybe not seen properly, so I'll make it a different color. Make it blue. So this function here is minus ut minus a. So when you add this one now, this one, add it to this one, you end up with so this one and this one I'm going to add up. Let's remove this one. You could see it better now. So I remove this one to here. So we are adding those two. Up to here, so sorry, I should have made a mistake. I should move that one. So that is, here is ut. And this is minus t minus a. So when you add those up now, this area up till t equal to 0, that's 0, that's 0, it's going to be 0. Different color, make it red. So after that, this function is one in between 0 and a. This is a, and this is a, and this is a. This is 1, this is 0. When you add them up, you're going to get 1 here. In this area, after t bigger than a, this is 1 and this is minus 1, isn't it? This is plus 1. When you add those two, you're going to end up with 0. Now this is pulse function. So I add this pulse function. Pulse function is ut minus ut minus a. So that's pulse function. Now I am saying if this is 1 and this is a, so I could use this pulse function in order to get this function. How I can do it? If you consider the time interval between 0 and 1, between 0 and 1, if you introduce a pulse function, unit pulse function is this, isn't it? If you multiply this pulse function with this function, that function here, 2t function, that means you are multiplying it with this pulse function. So you're going to get this only, isn't it? So that means after t bigger than 0, it's going to be 0, because the pulse after 1 is 0. Pulse before 0 is 0. So you're going to get this function only. So if I draw it here, right? If you do this multiplication, so this function here is this. Stop here, 2t. So if you do the second time, choose a different color now, make it green. Between 1 and 3, apply this time a pulse like that. This is minus 2t plus t is that function. So maybe I can draw it on top of it, that function. For this function, I am using that green pulse function. So that is the green pulse function is this, isn't it? As we explained here. Multiply it with this function, you only get this. Here, I can make it a bit bold here, you could see it. If you multiply the first, if you multiply this pulse function with this function, you're going to get that bold green here. The last one is this function is 2t minus 8. If you multiply this with a, make it black, if you multiply it with a pulse function like that, this is that pulse function, multiply this one, you're going to end up with this bold here. So what you get is this function. Conclusion is this: by using these pulse functions and the difference of pulse functions, difference of unit functions, get the pulse function. By multiplying the different pulse functions for different intervals, I can write a formula for a given function. So this is the utility that we use here are the unit functions. So I can represent some of the mathematical functions like that as a formula as shown here. Otherwise, you cannot write it as a formula like that. That is something that we will be using later on. That's why I explained it here. That's the end of this video then.